love foods, but what do we know about flavors?
What is flavor? Flavor is the sensation produced by a material taken in the mouth, perceived principally by the aroma receptors in nose and taste receptors in the mouth. Let's take a look at the first class, which is fruit flavor. The taste comes from the sweetness due to sugars and the sourness of organic acids. The aroma can distinguish the types of fruits. For example, citrus fruits usually rich in terpenoids, while non-citrus fruits such as apples usually characterized by esters and aldehydes. Vegetable flavors released when raw vegetables are chopped or cooked. For example, glycosides in celery and glucosinates in cabbage. The spice flavor. Spices are often used as essential oils and oleoresins in the food processing. The volatile compounds give the characteristic aroma. For example, eugenol in cloves and cinnamaldehyde in cinnamon. Moving on to the beverage flavor. Beverage flavor can be divided into three types. The first one, unfermented, such as fruit juices, milk, or coffee. The second type, fermented, such as tea or alcoholic beverages, such as wines. And the last type, which is compounded beverages, such as soft drinks or cordials. Meat flavor. Meats are usually cooked, dried, or smoked. The application of heat causes a reaction between amino acids and sugars, known as Maillard reaction. Next, for fat flavor, the unsaturation of fat leads to oxidative cleavage and the formation of both desirable and undesirable flavor. For cooked flavor, the non-volatile precursors such as Maillard reaction and lipid oxidation develop new flavors during heating in the presence of water. Empireumatic flavor. Imperial refers to being in a fire that is usually smoky and hotter than the boiling point of water. There are three major categories of empireumatic flavors, which are smoked, broiled or fried, and roasted, toasted, or baked. The last class is stench flavor. The strong aromas can be produced during microbial growth, such as the fermentation of cheese or the spoilage of foods. The air oxidation can give a rancid note to foods containing unsaturated lipids, such as fish or soybeans.
Flavor development during food processing.
The first one is caramelization. The heating of sugar at a prolonged high temperature will create caramelized flavor. The application can be seen by the manufacturing of candy where the sugars are intentionally burned to create the flavor, or by the boiling of maple sap to create a typical flavor of maple syrup. Amino acid thermal breakdown can be divided into four. The first one, enzyme activation, such as guanosine 5-monophosphate GMP, a flavor enhancer in vegetables. Second one, pyrolysis. Pyrolysis occurs when food exposed to a high temperature in dry environment. For example, baking and grilling process. The third one, Maillard reaction, that usually produce nutted, roasted, meaty, and burnt flavor. Browning is also occur on the surface of the foods that have been dehydrated by the heat source. Striker degradation produces little or no browning, as it is associated with Maillard browning. It is also leads to the formation of aldehydes. Lipid thermal breakdown is the autooxidation of unsaturated fatty acid that causes rancid odors of deteriorated fats and oils, while for thermal lignin degradation, phenols are the major contributor to the wood smoke aroma. The major components of wood, such as lignin or cellulose, will degrade to produce the flavor volatile compounds. The last one, thermal reactions of sulfur compounds can be observed by the aromas of cooked onion or garlic. The cooking method of onion or garlic will result in various flavors. For example, when a lot of water present during heating, thiosulfonates will produce di, tri, and polysulfides. But when very little water is present and the alliums are in lipids, the complex polysulfur compounds are formed.
Cinnamon is one of the common spices used in cooking, baking, and added to many foods such as toast and lattes. Cinnamon is a product from the tree of Cinnamomum genus. The bark of the tree will be sun-dried, and once dried it will be in the form of a rolled stick, or what we know as cinnamon sticks. Cinnamon can be classified into two categories. The first category is cassia cinnamon, which is more common. It has a rugged texture, darker color, rolled in thicker sheets than the next category, and it also comes with a more intense flavor. There are three specific types of cassia cinnamon, which are Indonesian, Chinese, and Saigon. Next category is Ceylon cinnamon. It is a bit more expensive than cassia cinnamon, has finer texture, rolled in thinner flat layers, and comes with a mild and delicate flavor. Ceylon cinnamon is referred to as the true cinnamon, and it is native to Sri Lanka. Cinnamon is rich in antioxidants that have anti-inflammatory effects that may help in lowering risk of disease. It also may reduce blood pressure, improve sensitivity to hormone insulin, and help to fight HIV. Besides that, it also comes with antifungal and antibacterial properties and can even reduce tooth decay and bad breath. One of the most important active ingredients in cinnamon would be cinnamic aldehyde. This compound is the reason behind the specific spicy aroma and flavor of cinnamon, and it is often used in flavorings and fragrance. Its structure is shown in the picture on the right. It is important to note that cassia has high coumarin content and could be highly toxic if taken in excessive amounts, and in worst case could even damage the liver. Ceylon, on the other hand, has a low coumarin content, so it does not cause much worry on toxicity. For the dosage, it is usually within 1 until 6 grams daily, but it also depends on the purpose of the intake.
To find out the compounds in cinnamon, we could apply gas chromatography mass spectrometry analysis. However, to do that, oil extraction has to be carried out beforehand. Usually, the method that will be used for oil extraction from the sample would be steam distillation. Steam distillation is a method used to distill compounds at a temperature lower than the boiling point, therefore making it especially suitable for the extraction of temperature-sensitive compounds. Oftentimes, steam distillation will be used for the extraction of essential oils from plant materials. GCMS is composed of a gas chromatograph and also a mass spectrometer. In gas chromatography, it would involve the usage of mobile phase such as helium, nitrogen, and hydrogen, and stationary phase which would be present in the column. For mass spectrometry, the main events that would take place would be ionization, acceleration, deflection, and detection. GCMS has been widely used not only in the detection of flavor compounds in food, but also in forensic toxicology, criminal investigations, and drug detection.
Why do we combine GC and MS?
The usage of gas chromatograph and mass spectrometer by itself can have certain disadvantages. By only using GC alone, it would be difficult to differentiate multiple molecules that have the same retention time, hence elute at the same time. Moreover, the usage of MS alone relies on the purity of the sample, and it could be possible for two different molecular fragments to share a similar ionization pattern. Therefore, by combining both GC and MS, we can reduce the possibility of error and increase the accuracy in identification. It will be highly unlikely that two different molecules will behave the same way in both a gas chromatograph and a mass spectrometer.
Analysis of cinnamon using gas chromatography mass spectrometry.
First off, the apparatus will be set up as shown in the diagram. Cinnamon will be grinded into powder form and placed into the round bottom flask, which acts as the distillation pot. The distillation pot will then be filled with water until about 2/3 full. The heating will be started slowly and eventually the mixture will start to boil and distill, causing water to be lost from the distillation mixture. Due to the reduction, a small amount of water will be replaced through the separatory funnel. As the vapor leaving the distillation pot enters the condenser, it will be cooled, causing conversion from vapor to liquid. Upon reaching the end of the condenser, the distillate will be collected in the round bottom flask. Bear in mind, an indicator of oil presence in the condensate is that the drops formed in the condenser will appear cloudy. Next, the distillate will be transferred into a separatory funnel where methylene chloride DCM will be added to extract the cinnamon oil. Once layers are observed, DCM layer and aqueous layer will be drained and collected separately in two flasks. The extraction will be repeated using the aqueous layer to obtain remaining DCM fractions. Once done, the DCM will be dried with anhydrous sodium sulfate to absorb traces of remaining water, and it will produce solid magnesium sulfate heptahydrate. Then the liquid will be transferred, separating it from the solid. Rotoweb will be used to strip off the DCM, and cinnamon oil will be obtained, ready to be used for the GCMS analysis.
For the analysis, we will start off by injecting the cinnamon oil into the gas chromatograph through an injection port at high temperature so that the sample will be volatilized and become vapor. Once volatilized, sample gas molecules will pass through a column via the carrier gas, which is also the mobile phase. The columns tend to be lined with stationary phase. The gas molecules being carried in the mobile phase will interact with the stationary phase. The high temperature of the oven will cause the molecules to separate as it travels through the column. The gas molecules with lower boiling point will come out from the column first. Meanwhile, the gas molecules with higher boiling point will come out from the column later, hence causing them to have different retention times. Upon entering the mass spectrometer, the separator compounds will undergo ionization at 70 eV, and it will cause the formation of molecular ions that may be fragmented into smaller ions. Each ion will have a specific mass to charge ratio. The ions will then be focused into a beam and accelerated into a magnetic field. Then it will be deflected and eventually hit a detection plate where the mass to charge ratio and the relative abundance will be measured. The mass spectrometer will provide the data through a mass spectrum. For identification of the compounds in cinnamon, the mass spectrum data obtained was compared to those from the NIST Mass Spectral Library and the published mass spectra.
Compounds detected in cinnamon.
Based on a research by Yu et al. 2020, at the end of the GCMS analysis, there were a total of 36 volatile components detected in the cinnamon oil. There were 6 aldehydes, 3 esters, 7 alcohols, 17 terpenes, 2 aromatics, and 1 ketone. Out of all, the most abundant volatile component was cinnamic aldehyde with a total of 73.345%. Some of the other components that were also detected would include 2-methoxycinnamaldehyde, cinnamyl acetate, benzaldehyde, and benzyl benzoate.